Good afternoon everyone, I'm Arnaud Camp. The aim of this presentation is to provide a general overview of the CENSE project, which was funded by the French National Research Agency and is drawing to a close. CENSE stands for Characterization of Urban Sound Environments, Modeling, Noise Sensors Network and Open Data. The reduction of the noise exposition represents both societal and environmental concerns, in particular for cities that are subjected to a multitude of noise sources and that count de facto numerous exposed people. Noise mapping is acknowledged as a relevant tool to diagnose urban sound environments, to propose action plans to reduce noise annoyance, as well as to communicate with city dwellers. Nowadays, noise maps are essentially elaborated by means of numerical simulations from a census of noise sources followed by a sound propagation modeling. This method has some well-known limitations, especially concerning the inaccuracy of input data, the simplified emission and propagation modeling, and, lastly, the inadequacy of classical output noise indicators to describe the perceived sound environments. In parallel, noise observatories have been deployed in some cities, which give locally access to the time variations of the real sound levels, but entail high operational costs that forbid their dense deployment. The CENSE project aimed at establishing a new methodology for assessing noise environments, combining open data, measurements, and modeling. This required more specifically to develop and implement a low-cost sensor network, to develop sound source recognition techniques, to improve noise mapping tools, to develop data fusion methodologies adapted to the problem of noise pollution, to propose representation of the quality of the noise environment, and we finally placed open science and standards at the heart of the project. The project involved 10 partners, namely Université Gustave Eiffel, WISIS Labs, Ville de Lorient, Labstic, CEREMA, LS2N, ETIS, INRIA, Bruit Parif, and Bouygues INS. The project, which is drawing to a close, has produced scientific and technological advances. This first presentation of a series of 5 will give a general overview of the project's comprehensive approach and framework and its operational outcomes. One will refer to the following presentations for details. First, the project has led to advances in modeling. All noise mapping achieved under the CENSE project relied on the noise modeling software, which has been improved and subject to a new release during the project. It is a free and open source software dedicated to environmental noise maps that implements the Knossos method. In addition, a specific process for noise mapping was developed under the project, based on the coupling between an open source noise mapping software and an open spatial database that can provide most of the input data for noise mapping. Then, a sensitivity analysis built on an open source modeling framework has been proposed. The study area retained all along the CENSE project is the city of Lorient. It covers an area of about 2 km² and more than 14,000 receivers. In brief, the study revealed that the most influential parameter is whether diffraction over horizontal edges is considered or not, and then the emission part of the Knossos method, and more in particular the mean flow rates of the road category, the closest to the receiver. Second, the project has led to advances in sensor networks. Modeling was indeed accompanied with the development of a high-density network of low-cost acoustic sensors based on wired and wireless transmission of spectral data. A first step concerned the development of wired and wireless low-cost sensors based on the MEMS technology. In order to study the acoustic behavior of the developed sensors, several tests were performed in an acoustic test room, which evaluated the linearity, directivity, sensitivity, and background noise characteristics. The conclusion of these tests is that the sensor appear to be acceptable for the frequency bands between 400 and 5 kHz. More than 100 sensors have been deployed on a smart lighting network. Then an IT infrastructure has been developed under open source basis and with respect to private life. Each node produces acoustic data, pressure level statistics, and third octave spectral data that are sent every 10 seconds. The storage architecture of the CENSE project was designed to maintain high availability. To this end, the data are distributed on two distinct sites. Each gateway node collects data through its sensors, then aggregates it into an embedded Open Sensor Hub instance. This aggregated data is transferred to a random server through a secured HTTP request using the open-source Elasticsearch interface. Acoustic data is pushed to the servers of Briparif that services a range of display tools available online. Higher-level data visualization and monitoring can also be performed using a Kibana interface. Third, the project has led to advances in meta-modeling and data assimilation. The CENSE project relied indeed on a two-step approach to combine measurements and modeling, namely the construction of a metamodel and its use under data assimilation techniques. The metamodel is built in three steps, namely the generation of the training sample, here 2000 simulations, dimension reduction through principal component analysis, and kriging of the projected values of the training sample onto the basis vectors of the reduced subspace. Once the metamodel is built, each call with new input parameters takes a very small amount of time, about 100 milliseconds, compared with 1 hour for the complete model. The idea of data assimilation is to correct the simulated noise map thanks to the additional information brought by the observations. Unfortunately, for phasing and data availability reasons, the model was built on data produced on the city of Paris and not on the Lorient measurement network of the CENSE project. Among all the data assimilation approaches, we compared state estimation, inverse modeling, and a joint state parameter estimation. The state estimation applies a direct correction on a simulation map, assuming that the simulated map is an a priori map with some unknown error at every point of the map. The inverse modeling does not correct directly the simulated noise map, but instead the input parameters of the noise model, or in our case, the metamodel. Joint state parameter estimation combines both approaches. Methods were compared through a leave one out cross-validation. An interesting result operationally is that we showed that this method is suitable for areas where no traffic nor weather ground measures are observed. And fourth, the project has led to advances in advanced sound environment characterization. Indeed, going further than just the sound levels, the data collected through the urban sensor network allow to perceptually characterize the soundscape. The sound quality and the noise annoyance has been assessed for both the pedestrian and inhabitants' points of view, thanks to a questionnaire that has been sent by postal mail, from which we got about 300 responses. Outdoor pleasantness and outdoor annoyance models were built. Overall loudness, rated on a noisy silent scale, appears in all models at the first place, showing that this variable is the most influent one. Sound sources such as road and air traffic, expressive voices and birds also appear in the regressions. Finally, it is found that noise sensitivity and age increase the adjusted explained variance of the models. As these perceptual characteristics depend on perceived sources, we also focused on the possibility to measure automatically the sound source presence ratio on the sensors in addition to classical levels indicators. The calculation of the source presence ratios have been automatically implemented on the low-cost sensors for relevant sources such as road traffic, two-wheel motor vehicles, voices and birds, for example. The source identification is realized every second for each source of interest on each sensor. Source identification is conducted using a deep convolutional architecture that first extracts time-frequency patterns relevant to the identification of sound sources from each 1 second third octave segment. Results from the algorithm are in accordance with expectations. To highlight the results on a map, a cartographic portal has been set up, publicly available online. One can draw scientific conclusions from the CENSE project as it is drawing to a close. The project permitted advances on enhancing the noise map production process and proposing a sensitivity analysis for noise mapping, designing and deploying a low-cost sensor network, as well as data archiving, proposing data assimilation techniques applied to sound levels prediction, and characterizing urban sound environments through sound recognition and perception advances. The main encountered limitation consists in the technical difficulties linked to the sensor network maintenance, which has desynchronized part of the perceptual study from the physical data collected, and necessitated that the work on data assimilation be done on another measurement network. The CENSE network being now operational, it will allow researchers to answer many scientific and technological questions regarding the characterization of the urban sound environments. Finally, the CENSE projects open up many avenues of research, for example on the enrichment of the input data with other sources of traffic and acoustic data, on the production of perceptual noise maps, or on the use of sensor networks for decision making. Thank you for your attention. One can refer to the next presentations or to the publications from the project for more details. My colleague Judicael Picot and myself will be happy to answer your questions, and we hope that the session will stimulate reflections on the characterization of urban sound environments. Thank you.